So, two-stroke cycle, what happens? Okay, two-stroke cycle PV diagram will be like this. And before previous diagrams, what I have done, that is ideal cycle. Practically, there will be certain differences, but we are not going for the details. But those are ideal Otto cycle or diesel cycle, four-stroke cycle. Okay, and for two-stroke cycle, what happens when 1, 2, 3, 4, when process is happening, let us say compression stroke happening. So, during compression stroke, when piston is reaching towards TDC, so in between there will be spark. Okay, spark will be happening and combustion will be taking place. When piston is going for power stroke, so nearby end of the power stroke or nearby BDC, exhaust port will be open. So, some air fuel mixture will be entering there and gas will be entering. So, some mix up will be possible. There is no extra idle stroke. Idle stroke means that horizontal line I had drawn for 4 stroke. Okay. Okay, this is called idle stroke. Idle. Okay, the horizontal like one for exhaust, one for entry, compression, power, compression, combustion, power, again exhaust. Those strokes are not there in two-stroke engine. So, what happens because of extra idle stroke not there? So, entry of air fuel and burned gas, those mixing are possible because we do not have any extra stroke. So, what happens because of that, some fuel and air mixture will go through the tailpipe. Okay, if you see autos are making lots of noise and lots of smoke coming, that means that may be two-stroke engine because incomplete combustion happening. Because of that, some fuel and air mixture going out from the tailpipe. So, their fuel efficiency will low, that is they are giving lots of pollution also. So, that is harmful to the environment. Okay, but two-stroke engine can be smaller engine. Okay, smaller engines. Okay, but four-stroke engine will be very heavy, like for example diesel truck or car or train. The locomotive engines, those are also four-stroke engine. Four-stroke is a little bit heavier, but it will have more fuel economy and good for pollution. So, fuel air mixture. So, whenever you are having any chemical reaction, so chemical reaction, it will take certain amount of air. Anything? Okay. Okay. When you are taking certain amount of air and fuel mixture, it will be burning completely. So, burning completely means exact amount of air you have to give. Air means oxygen, so that there will be no extra fuel or extra air. So, if you are giving less amount of air, so extra fuel will be there. That means some fuel particle will not burn and you will not get that much of energy. But if you are having higher amount of air, so in that case fuel will be burned, but some air will get heated up, that unburnt air, and that will take certain amount of heat. So, that heat you can reduce. So, very high amount or very low amount of air is not good for your system. So, you have to give proper amount of air and fuel mixture, that is called stoichiometric ratio. Okay. So, for that I have one diagram, power and air fuel ratio. Okay. So, you get higher power here. Okay. This is a rich mixture. Rich mixture means higher amount of fuel is there. So, higher fuel. Lean mixture means less fuel. Okay. So, less amount of fuel this side and vertical line, so proper air fuel mixture. So, little bit rich mixture will give higher power because all fuel will be burnt. Okay. This is power curve. Okay. And for normal operation, 15:1 for normal hydrocarbon burning in IC engine, 15:1 will be normal ratio. It may be more or less also based on your hydrocarbon property. Okay. Whenever you are talking about IC engines, so we should know some definitions also. So definitions are like this. First I have to draw the figure. 1, 2, 3, 4. Doesn't matter which sequence I am writing. When you are whatever numbering method you use, you should use uniformly. Okay. So compression ratio equals R equals V3 by V4, cutoff ratio. RC equals V1 by V4, expansion ratio. Expansion ratio equals RE equals V2 by V1. Okay. So, this formula maybe you can use later, but you should remember. Okay. So, there is one problem. An Otto cycle has maximum temperature 1200 Kelvin and exhaust temperature. So, Otto cycle I have to draw first. Okay. Otto cycle, if I have to draw, it will be like this. Okay, 1, 2, 3, 4. If I want to draw diesel cycle, it will be like this. Okay. So, present problem is for Otto cycle. Okay, but for diesel cycle also you should practice. 1, 2, 3, 4. This point is 4, and if I want to draw the same thing in TS diagram, it will be like 1, 2, 3, 4, 1, 2, 3, 4. Okay. Now, at the beginning of the compression stroke, the pressure and temperature given 1 bar, and temperature is given 27 degrees centigrade, means 300 K. So, all unit must be checked. Okay. The compression ratio you have to calculate, V1 by V2 you have to calculate, and specific heat ratio is given 1.4. Okay. If it is not given, you should assume this value. So, T1, T3 is given 1200 K, T4 is given 600 K, P1 is given. So, V1 by V2 adiabatic, so T2 by T1, 1 by gamma minus 1. Okay. So, and V3 by V4 equals V1 by V2 actually equals T3 by T4 gamma by gamma minus 1. So, this will be giving V1 by V2 equals 1200 divided by 600, 1 by gamma minus 1 equals 5.65. Now, if I want to find T2, so it will be like T2 divided by T1 equals T3 by T4, implies T2 equals T1 into T3 by T4 equals 600 K. Okay. Gas turbine. So, gas turbine means it is also internal combustion engine, but it does not have any piston like reciprocating piston, crank or connecting rod, and there are different sizes of gas turbines available. One micro turbine, micro does not mean that it will be like millimeter or micrometer. It is a micro turbine less than 50 horsepower power. If it is producing, then it is called micro turbine, and it can be like 50, less than 50 to large turbine for industrial applications. And it is open cycle, like gas compression will be happening, burning, and exhaust will be there, but there will be no complete cycle. In IC engine, your system were complete cyclic. Okay. In gas turbine engine, this is used in aircraft engine. You can remember the aircraft wings will have engines. Okay, air entering and it is going out. So, the same air is not being used. Okay, that's why it is open cycle. This is called Brayton cycle. Brayton cycle, how it is working, I will explain. Adiabatic compression. So, it will have one compressor, you see this, and one turbine. Okay. So, air will be entering here, air entering, then air after compression it will go to one combustor or combustion chamber. Once combustion happening, the hot gas, burnt gas will be entering to turbine. From turbine it will go to exhaust. Okay. Aircraft engine, like if you see top diagram, air entering and hot gas exiting. Okay. Now, what is compressor? Compressor is like, it is not like reciprocating compressor, it will be like centrifugal or axial type compressor. That compressor will be compressing air, because the combustion chamber is higher amount of air. So, to get higher amount of air, actually you compress and you give condensed or compressed air into combustion chamber or combustor. So, from there hot gas, high volume gas, you pass through one turbine. So, normally it will be like axial turbines, and compressor also normally axial compressor, and the centrifugal compressor also possible. So, axial turbine, axial compressor they will be using. Okay, and compressor will be run by your turbine. Okay, there is no piston cylinder arrangement, there is no crank arrangement. So, it will have turbine, compressor, this is the main component, and other component also possible, but these are the mains. Okay. Now, if I draw a diagram for this one, how things are working, PV. So, initially 1 to 2 compression will be happening, 1 to 2 compression will be happening. Okay, you see the diagram from here, and 2 to 3 combustion happening, 2 to 3 combustion happening, and 3 to 4 actually expansion happening. The hot gas whatever you are getting, high pressure and high temperature gas, again high pressure and high temperature. Okay, high temperature, high pressure gas you take, and expansion will be happening. Okay, so not this direction, this will be the right direction, 3 to 4. Okay, and after 4 to 1 actually normally we do not show any line because the same air is not entering or same exhaust thing. Okay, so cycle is that 1 to 2 will be compression, you take air, you compress it, put in combustion chamber separately, then same air or high temperature and high pressure gas you pass through turbine. So, this is turbine. Okay, this is compressor. Okay. And if I draw a TS diagram, it will be like this: 1 to 2 compression process. So, adiabatic compression, PV gamma equals constant. 2 to 3 heat addition, lots of heat will be given, temperature will be high, very high at 3. Okay. Then expansion also, PV per gamma equals constant or entropy constant. Okay. So, 3 to 4. Okay. So, normally you do not connect this one, and whenever you are drawing to compressor and turbine, you have to follow some rule. The compressor means you are compressing. Okay. So, that is why you draw like cone shaped compressor. Okay. If you draw opposite way, let us say you are drawing compressor like this, okay, and shaft and turbine like this. So, what is happening? So, gas is you are taking and exiting like this. So, like gas is expanding, but in compressor you are actually compressing. So, this figure is wrong, it will be like this. Okay. So, gas entering, compressing, and turbine gas expanding. So, expanding means in size in increasing. So, that way we draw. Okay. If you draw opposite way, this will be wrong, this will be wrong. Okay. So, 2 to 3 actually isobaric process, at same isobaric process. Okay. And 1 to 2 isentropic process, 3 to 4 also isentropic process, and it is very fast process, continuous process. So, it must not be isentropic. Okay. So, we are assuming these are adiabatic process 1 to 2 and 3 to 4. Thank you very much. Today I am finishing this 12th lecture. I hope you have learnt well in this course. Thank you very much.